Hi, my name is Yusun from Tsinghua University, China. Today, I would like to introduce our work, Confidence-Bounded Replica Currency Estimation. Let's start with an example of Singles Day Global Shopping Festival, which is an annual promotion event held on November 11th by Chinese e-commerce platforms. Since the surplus goods are limited and the first dozen of customers who place orders after 0 o'clock can get extra discounts or gifts, a large number of customers will be waiting for the event to start. Therefore, a large number of orders will immediately appear at 0 o'clock. As reported by Alibaba, there are more than 4,900,000 sales transactions per second during the 2018 Singles Day Global Shopping Festival. Such intensive workload requires the e-commerce systems enable high throughput and low latency. Meanwhile, data currency is also very important since customers need to know the current surplus of goods. Systems must ensure that the customer's orders have corresponding goods and all the surplus goods are available for purchase. Distributed databases are used to process such large amounts of data, where distributed data stores with replication, such as Bigtable, HBase, Dynamo, and Cassandra, carry different versions of a data item, where timestamps or global version numbers are used to determine currency. The motivating example shows a cluster with replication factor 4 running across multiple data centers. A read request is expected to return the most recently written version v24, the fourth version stored in replica R2. Unfortunately, this does not always occur due to system availability and network partitioning, and the response replica with the stale version v44 may be returned as a result. Therefore, in order to ensure data currency, existing systems such as Cassandra considers different consistency levels and wait for a fixed number of replicas to respond with respect to the success of read or write operations. All consistency level waits for all replicas to respond and ensures the consistency of returned results. However, although stronger consistency provides improved guarantees of data currency, it increases latency and decreases throughput, which is undesirable in many real applications. Quorum consistency level requires fewer replicas to succeed read or write operations and wait for more than half of the responses. However, considering the aforesaid intensive workloads, it still has an undesirable latency, and the client has no information about the currency among responding replicas. One consistency level immediately returns to the client as long as one node responds. To handle the aforesaid write-intensive workload, such as Singles Day Global Shopping Festival, the write consistency level 1 is preferred to provide low latency and high throughput. However, the remaining replicas cannot guarantee immediate and perfect consistency. In this case, with the read consistency levels 1 or quorum, the returned replicas may be stale. Thus, it can be seen that existing solutions fall short in two aspects. Firstly, the client has no information about the currency among responding replicas. Secondly, the consistency level is tuned with respect to the number of responding replicas rather than the likelihood of returning replicas with current values. Therefore, we propose a new read consistency level dynamic. It provides theoretical bounds on the confidence of replica currency estimation. For example, as shown in the figure, v44 could be estimated to be stale with the corresponding confidence. Moreover, dynamic immediately returns the responding replicas if the currency thresholds are satisfied, rather than relying on a fixed number of replicas to retrieve with no guidance on the currency results. And it enables systems a tunable confidence level of replica currency, such that the system intelligently determines the number of replicas to retrieve. In summary, in order to provide low latency and high throughput, read consistency level 1 is preferred in real distributed systems. Since existing read consistency levels wait for a fixed number of replicas to return and have no information about the responding results, we devised a novel dynamic read consistency level which enables systems efficient and user-intuitive. Actually, designing such a novel read consistency level is challenging. While efficient learning models are directly applicable, we expect a guaranteed confidence for the currency estimation in order to make it more reliable. It's highly non-trivial to derive a lower bound of the probability about whether the replica is current or stale, with respect to the ground truth. The problem becomes even harder given that the replicas are distributed across cluster nodes with limited synchronization. Our currency prediction models need to be learned locally in each replica node, such that they are small enough to propagate to the other nodes with low overhead. In this work, our major contributions are deriving theoretical bounds for the replica currency estimation confidence and enables a novel read consistency level dynamic. Considering the challenges of directly estimating the replica currency in realistic scenarios, we first consider an idealistic scenario. For example, in figures A and B, the full update history is available in replica R4, which could be used for model learning and currency estimation. Figure A shows that version V5 is the latest version with timestamp T5 from responding replica R4. However, if there is a version V6 written to replica R2 with timestamp T6, which is less than query time zeta and has not responded, then V5 is a stale version. In contrast, figure B shows that if there is no write between T5 and zeta, then V5 is current. In realistic scenarios, writes are not propagated to all nodes, and the models are learned locally at each replica node. Figure C shows V44 is the latest retrieved version with timestamp T44 at response replica R4. Since there is a version V24 written in replica R2 with whose timestamp is greater than T44 and not greater than zeta, and the replica R2 has not responded, then V44 is stale. On the contrary, in figure D, there is no version between T44 and zeta. That is, V24 has not occurred and V44 is current. Rather than directly predicting the timestamp of the next version, it's more reasonable to train a model over the time distance to the last version. That is, we consider the time distance tk of replica version vk to the previous version vk-1. Since the data may be skewed, it's more intuitive to apply a machine learning model for prediction, rather than basic statistical analysis. This figure illustrates the Bayesian model for prediction. The model predicts tk referring to the previous time distance tk-1. We use a simple linear regression model for three reasons. Firstly, its generalization error is bounded, which serves as a foundation for the confidence guaranteed replica currency estimation. Moreover, the model is small enough to be propagated among the nodes, and it can be efficiently trained incrementally as new versions arrive. Based on the predicted timestamp Tn plus 1 prime of the next version Vn plus 1, we estimate the data currency of the last retrieved version Vn. Figure A shows that if the predicted timestamp T6 prime is greater than the query time zeta, we consider V5 to be current. Otherwise, in figure C, if T6 prime is not greater than zeta and the replica R2 has not responded, we consider V5 to be stale. The corresponding confidence could be calculated based on the generalization bound of Tn plus 1, as shown in figure B. If the query time zeta equals to the lower bound of Tn plus 1, Tn plus 1 will be greater than zeta, and the corresponding confidence is thus obtained. Similarly, if the query time zeta equals to the upper bound of Tn plus 1, Tn plus 1 will be less than zeta, and the confidence is also guaranteed by its generalization error. To estimate the currency for the observed replica version VPN in realistic scenarios, We also need to predict the timestamp TQM of unseen Watson VQM, namely TQM prime. Specifically, we predict TQM prime for each invisible replica RQ that has not responded to the query, since there may exist multiple Watsons of RQ that are invisible to the responding replica RP after the last synchronization TQW, for example V23 and V24 in the figure. We iteratively apply the prediction starting from the known Watson V22 of the last synchronization by estimating the distance between adjacent time intervals. Similarly, the corresponding confidence bounds can be derived by iteratively applying the generalization bounds of prediction models. Based on the predicted timestamp TQM prime of the unseen Watson VQM, we estimate the data currency of the latest Watson VPN. In Figure A, since the predicted timestamp T24 prime is greater than zeta and the T23 prime is not greater than T44, we estimate the retrieved Watson V44 to be current. On the contrary, in Figure C, since the predicted timestamp T24 prime is between T44 and zeta, V44 is estimated to be stale. Referring to the generalization bound of TQM, the confidence bound of currency estimation could also be obtained. As shown in Figure B, if the query time zeta equals to the lower bound of TQM, zeta is less than TQM, and if TPN equals to the upper bound of TQM minus 1 is greater than TQM minus 1, the confidence of current estimation is thus obtained. Similarly, we could also calculate the confidence of stale estimation by considering the generalization bound of TQM with TPN and zeta. In realistic scenarios, there may exist multiple replicas that do not reply. The estimation and confidence from each invisible replica may not be equal, and we aggregate this currency estimation on the latest Watson VPN as well as their corresponding confidence values. For currency, only when all the invisible replicas estimate VPN is current. For example, in Figure A, we conclude VPN to be current. We aggregate the corresponding confidence values over all the invisible replicas that have a current estimation. Intuitively, if there exists one invisible replica RQ that estimates VPN is stale, for example R2 in Figure B, is sufficient to conclude a stale estimation. The confidence is also calculated by combining the estimations of all the invisible replicas that have a stale estimation on VPN. In experimental study, we evaluate our prediction models against the SOTA deep learning model TLSTM and the probabilistic approach PBS. As shown in the figures, while more complex models TLSTM may outperform for larger training rates, our models achieve comparable accuracy but with much lower overhead, and our models achieve higher accuracy than PBS as our work models write error rates locally at each node. We further evaluate the performance of dynamic consistency level by comparing against the existing read consistency levels 1 column and all with 1 write and with column writes. Figures A and C report the accuracy of returning current replicas in query answering. As expected, as we increase the confidence threshold, the accuracy of returning responses increases and the corresponding time cost increases as well. The experimental results show that dynamic is almost as accurate as the strong consistency settings, while much more efficient. Finally, we conclude that our work studies the confidence-bounded replica currency estimation in distributed databases, which enables a novel dynamic consistency level. It makes systems efficient and user-intuitive without introducing large overhead during query processing. That's all about our work. Please feel free to ask me questions. Thank you for listening.